All right, so 2 weeks left of the course, so we're getting into the finishing stretch here almost. So today we will finish off medium access and then talk a little bit about the local area networks and Ethernet in particular, and a little bit on how one can use switches and hubs and so forth to build extended local area networks. So short review, what we talked about last week was a lot about medium access control, and one medium access control we talked about was ALOA. So for that, or for any medium access control, we would like to have a nice normalized throughput. Okay, so what is that? Well, it's the average number of successful transmitted frames normalized with the frame duration. So the best we can hope for here is to transmit 1 frame per frame duration, because we share the medium. So if we want to avoid collisions, we can at the most we can hope for is to transmit 1 frame over the medium and then the next frame and so forth. So there are no collisions, that they really butt together. Then the normalized throughput is 1. Now, this requires some coordination, and sometimes this coordination is difficult to do, especially when we have long propagation delays over the network. So typically we cannot achieve this. But anyways, so if we let S be the normalized throughput, it's the average number of successful frames divided by the frame duration. And we can write that also as the average number of transmitted frames. Okay. So not necessarily those that successfully reaches the destination, but all the attempts. Think of these as the average number of attempts per frame duration. Let's call that G. And then we multiply with the probability of success. So that's one way to do that. And if we do that for ALOA, the simplified analysis reveals that S is related to G in this way for the unslotted case, and in this way for the slotted case. So basically you see G here is the factor we had in the beginning, and e to the negative 2g is the probability of success for unslotted, and e to the g is the probability of success for slotted. And of course, whatever s we get here will be less than the maximum achievable one, and the maximum achievable one is easy to figure out, that it's 1 over 2e for unslotted and 1 over e for slotted. So this is nice equations, but one should realize that this is a simplified analysis, right? So there are some things that we have not really tackled here, but it gives at least an idea about what type of throughput we can hope for in the best of cases, namely 1 over 2e or 1 over e. So 1 over e is basically one third, more or less, right? So only 1/3 of the frames, I mean the maximum we can hope for was 1, but here we get 1/3. All right, so to improve on ALOA we can use something called carrier sensing, and it's basically listen, that is sense the channel for ongoing activity before we transmit. So that's the main idea. So sense the channel, if idle transmit, if busy back off. So that's the main rule for CSMA. What to do when we back off here, there are 3 main ways to do that, or maybe 2, depending on how you look at it. So the back off strategies, there is this persistent one, where, okay, so when the channel is busy, the station that has some frame to transmit cannot transmit because it's busy, but then it listens to the channel continuously, and as soon as the channel becomes idle, then it transmits. So this is an aggressive back-off procedure. It's really no back-off, actually. We can do non-persistent, which means that when we sense the channel as being busy, then we back off, that is, wait for a random time before sensing again. And of course, the longer this random time is, or the interval that this random time can take on, the more sort of cautious we are. And we are more polite in a one way. P-persistent is something in between, which means that we sense repeatedly, and as soon as the channel becomes idle, then we do, then either we transmit or we don't, and the decision is made with a certain probability. So if I'm in back off and sense the channel and the channel is idle after some time interval, then I draw a random number from a random number generator, and depending on the outcome, I either transmit or don't. And the probability for transmission is this P parameter. So depending on what P is, we can be more or less aggressive here. So when P is equal to 1, for instance, we're back to the persistent case. So P persistent is somehow a trade-off between persistent and non-persistent. It's not really exactly, but one can think of it like that. All right, another tweak to CSMA is that if we have a medium which allows for collision detection, and there are certain mediums that does that, in particular, if we have a wired medium, then this is possible if we do the electronics correct. And then what happens then is that when a station transmits a frame, simultaneously that station listens to the medium while transmitting, and if the medium contains data which is not what the station is transmitting, then it knows that the collision has occurred, right? So if I put out a 1, 0, 1, 0, 1, 0, and I don't get that sequence of ones and zeros, then I know that something bad has happened, a collision. So immediately when this is detected, we abort the transmission. Or rather, as soon as a collision is detected, we wait a little while and then we abort. And this waiting is just to make sure that other nodes which are listening to the medium also will have the chance to detect the collision. Because the collision is detected by detecting the presence of another ongoing transmission. Okay. So CSMA and ALOA and so forth, these are known as what should we call it? Random access protocol, or they are a little bit loose in their coordination, right? They rely on probabilities and detecting collisions through the loss of acknowledgements or by listening to the medium and so forth, and then try to recover from that. There is another approach which is called reservation protocols, and the idea here is that we would like to make sure that there are no collisions. So we pre-plan the transmissions in order to avoid collisions, rather than just to transmit and then recover when there is a collision. So here for the simple reservation protocols, we organize transmissions in cycles. And these cycles can possibly have different lengths. It depends a little bit on the exact protocol. So what is a cycle? Well, a cycle consists of two parts. One is a reservation interval. It's a duration of time where we organize transmissions. Okay, so this, we can think of this as some type of organization interval. And here we organize that by transmitting data, control data in mini slots. And then after that, there is the actual transmission of data frames, and we call that slots. So each data frame is transmitted in one slot, or sometimes it's also multiple slots, depending on the protocol. But anyways, there is some reservation and then some data transmission. And the reservation interval is then used by the users or the stations that are using the media in order to reserve data transmission slots, either centralized or in a decentralized fashion. The problem with this is that since the reservation interval is used to coordinate transmission, we also need to coordinate the transmissions in the reservation interval, right? Because we use the medium in order to coordinate how to use the medium. So it's sort of like almost a chicken and egg problem here. So we need some medium access control for the reservation interval also. Okay, and then there are several approaches, and one way is to use what's known as static channelization. We'll see a few examples of that in a short while. And that's, for instance, if we have these medium slots, we can divide the channel into time, TDMA. We'll see what that means in a second. So basically, if we have this channelization, it means that every user has a predefined time slot in the reservation interval where that station declares its willingness or its wish to transmit or not. So somehow we have already divided up the mini slots among the users in some pre-arranged agreement. Okay. Another way is to not do that and simply use random access in the reservation interval. So we use, say, slotted ALOA, for instance, or ALOA or something like that, or CSMA if you like, in order in the reservation interval only. And those, the data which goes through here is then used to organize the, these reservations are then made, and then we can use the data, transmit the corresponding data frames afterwards. Okay. And there are pros and cons with this. The problem with static channelization is that if you have many users, you need many mini slots, regardless if these users have a lot of data to transmit typically or not. So when you have many users with not a whole lot of data per user to transmit, then the users are typically not transmitting in a cycle, and therefore we just waste resources in asking these users whether they want to transmit or not. If we have random access instead, we can make the few users that have some data to transmit to contend for the channel during the reservation interval, and we can make the reservation interval smaller, and then the overall efficiency goes up. Because the reservation interval is just overhead, right? It doesn't necessarily bring in, it's something that we pay in order to have organized transmission. There is also polling is another way to do organized transmission over a medium. And then one can transmit, either we have a centralized controller that goes out and asks each of the stations whether they have some data to transmit, or we have some type of transmission agreement, a token. So if I have the token, I can transmit, and when I'm done, I pass it on to the next person on the on the medium, and that station can then transmit and then passes on the token and so forth. That's another way to organize here. And if the reservation are successful, then there will be no collisions. So questions, so forth? Okay. Channelization then. Okay, so what do we mean by that? How do we create channels? With channels here, we mean access to the medium in some way. So a channel resource can be viewed as an area in the time frequency plane. So if we have time along this axis and we have frequency along this axis, in a rectangle of t by w, we can transmit the number of symbols here. And the number of symbols we can transmit here has to do with the time and bandwidth. And in fact, it's 2wt, at least when this rectangle becomes fairly large, then it's 2wt. And why is that? Well, we know from the Nyquist criteria that if we have w hertz in channel bandwidth, the maximum symbol rate we can transmit without any intersymbol interference is 2w, right? So we can transmit 2w symbols per second. Okay. So what does that mean? We can transmit, for each second we can transmit 2wt symbols, and if we have t seconds, then we can transmit 2w times t symbols, 2wt. Okay. So the total resource in t in a time interval is then proportional to the product of w and t. For QAM, where we have complex symbols, we can transmit wt complex symbols inside this rectangle here. And the reason for that is that we can think of QAM as we're having two PAM processes, one in the I plane and one in the Q plane. So it's a complex symbol consists of two real valued symbols. So it's 2wt real valued symbols here, which is the same to say as WT complex valued symbols. Okay, so now a little bit more practical perhaps. So suppose we have some system bandwidth, W, and then we divide that into the green channel, the red channel, and the blue channel, and we hand out the green, red, and blue channels to users, to stations. And a station can then use the green channel here as at any time that station pleases, right? And since these channels are not overlapping, there will be no collisions here. Okay, so we split the system bandwidth into M frequency channels in general. So if we have M stations, and then each frequency channel is handed out to the users. There are then M users in total. Okay, so if we look at the bandwidth for one user is W over M. So what is the symbol rate for that user? Well, it's twice the bandwidth. That is twice times W divided by M. Okay, so that's how many symbols per second that user can transmit. And then during T seconds, how many symbols can we transmit? Well, it's 2W divided by M times T. Or the end result is that the symbol rate per user is 2W divided by M. Okay. We can also slice up the cake in the time domain rather in the frequency domain. So here we have the green channel, the red channel, and the blue channel. And the green user can use the entire system bandwidth, the whole W, but only on during a time slot. Okay, and the duration of the time slot is capital T divided by M. Okay, so we have the green, red, blue, green, red, blue, etc. Right? So what is the symbol rate we can have here? Well, when during the slot, the time slot, the users can transmit with a symbol rate which is 2 times W. Okay. But it can only transmit during a fraction of the total time, namely T divided by M. So each slot can then carry 2W T over M symbols during T seconds. And then if we want to calculate the symbol rate, it becomes 2W divided by M. Okay. And this is the same as in frequency division. So it doesn't matter whether we split up the channel resource in frequency or in time, we get the same average symbol rate per user. Okay. The difference here is that the users here transmit momentarily with a high data rate, namely 2W, but then has to be silent until it's the green user's time again. Questions on this?
Could you split up in both the frequency and time?
Absolutely. So I mean, typically this is done in LTE and in many systems where you have a split up both in time and frequency, and a user is handed out a time frequency slot like this. Okay, but again, there is no gain. There is no particular gain in slicing up the cake in one way or another. So it's for practical reasons we do this. Okay. Now there is actually, surprisingly enough, a third variation to do this. It's called code division, and this is used in 3G among other things. It's also used in Bluetooth. And the idea is that we use signals which are actually overlapping in time and frequency. So they are colliding in the sense that they are active at the same time in the time frequency plane, but they can still be separated from each other. So it can be shown that users can be separated, and this is exploited in these code division schemes. So I won't go into the details here, but the fundamental limits are still the same. So time frequency block can carry at most 2WT non-interfering symbols in this case. So there is no magic here, it's just another way to do that. to use the time frequency plane for different users. And one simple example of how this works could be like, for instance, if we have a blue user here, which is allowed to transmit this signal, and then we have a red user, which transmits this signal here. Then these signals exist, okay, and this is time. These signals exist during the same time, but if you look at them, they're orthogonal to each other. That is, if I multiply the blue with the red and integrate over time, I get 0. Which means a consequence of that is that if we have a matched filter to the blue signal here, and the received signal is red, the output of the matched filter is 0. Okay? While the output to the red matched filter would be the amplitude of that pulse here, plus or minus 1 if it's binary transmission. Okay. So we can have pulse amplitude modulation processes in parallel as long as they have orthogonal pulse shapes, and they can be perfectly separated at the receiver, even though they overlap in time. And one can also show that they overlap in frequency. Okay. So that's the good story. The bad story is that it doesn't matter because we can still not gain anything compared to TDMA or FDMA in its simplest form. So the reason why 3G wanted to go code division has to do with other things which are outside the scope of this course. Okay, so to finish off the channelization here, so the choice of method for channelization, time division or frequency division or code division, are based on other factors than pure data rates per user. It's implementation issues and other issues. In practice also, we need guard bands in time and frequency. Here we need a little bit of guard interval between time slots here, and the reason for this is that users must be synchronized when we do TDMA, and sometimes the clocks are not perfectly aligned with each other, so there is some synchronization error. And then also there could be propagation delay differences between the signals as we had in slotted ALOA, if you remember. Then we also need guard intervals here. The same goes for frequency division. So the local oscillator would puts out the mid frequency of the green user is not typically synchronized perfectly with the local oscillator for the red users. So their frequency slots slide up and down a little bit, and then we need a guard interval between them. And also, since there is no perfect band limited signals, transmission in the green slot here will leak into the red and blue slots to some extent. Okay, but we can keep that relatively small by good engineering. Okay, so these are practical concerns, some of the practical concerns that needs to be taken into account. And also, as we mentioned earlier here, practical systems are often hybrids. Okay, so we use typically time division and frequency division to create channels. And then actually these could then be used for some type of code division actually on top of this. Pure code division is used, for instance, in 3G and Bluetooth, for instance. One is based in time, another one is based in frequency hopping. So questions on this before we continue? Okay. So when we did all this medium access control, what we talked about, we already always more or less used time division as our main example. But we can do the same type of ideas in frequency division if you like. You just basically turn the graph upside down like this, and then you have it in frequency instead. It really doesn't matter that much. Okay. Okay. So, pros and cons with this static channelization. What is good? Well, it's very efficient for constant data rate services because we hand out these frequency channels or time slots, and these can be kept for a long period of time. Think, for instance, regular FM broadcast. P1 is always at that frequency, we know that. There is no need to reorganize that. And it's very simple. The drawback with this is that if we have certainly more or less data from one of the users, it's hard to share, to use the whole system resource. So for instance, if, that's maybe a bad example here, but suppose we have radio then, P1, P2, P3, and P4, and they share the spectrum equally, right? So then each of them have a quarter of the system bandwidth. But then suppose that P1 has a lot of data to transmit, while 2 and 3 and 4 has no data to transmit. So they don't have any data to transmit. But user number 1 can only use a quarter of the system resource regardless, right? Because the other 3 are already pre-allocated to some users which are not using it. Okay, so it's quite inefficient in that sense. The good thing would be to do then is to take the whole system bandwidth and give it to the first user until the first user is done. And then we reallocate the system resources. Okay. So that's a drawback with this fixed channelization. And basically the same thing to say that if we have bursty traffic, meaning that the user who wants to use the medium sometimes have a lot of data to transmit and sometimes nothing, then it's hard to cope with this in an efficient way. Okay, we can still cope with it, but it's just inefficient. So these dynamic multiple access control, like CSMA, ALOA, and so forth, they are more flexible and more attractive for bursty traffic. So that's why we see them quite often in data networks. And data networks could be anything from like your Ethernet to your Wi-Fi or Bluetooth or LTE, for instance. Right. Okay, questions? No? Okay, so let's continue. So now let's look a little bit on local area networks. So remember our journey now. We started with the physical layer at some point, and then we talked about medium access control, how to access a physical layer. And now let's assume that we have that cleared out. But now we would like to build larger networks, not networks consisting of several nodes sharing a medium, which we already touched on, but we also would like to connect those local area networks with each other. So that will be the topic of today's lecture. So what is a local area network? Well, it's typically a physically small network, meaning that the distance from one node to another, say, well, maybe less than a kilometer. I don't know. It's at least not thousands of kilometers. It's a relatively short distance. And typically these LANs are also used over some type of broadcast medium. Okay. With broadcast medium, I mean a shared medium. So we need a medium access control scheme for this. So Wi-Fi is a typical example of a local area network. So you attach to an access point, and that access point has some coverage region, tens of meters, maybe up to 100 meter maximum or something like that. So that's your local area network. And all the Wi-Fi transmitters which are in range of that access point or attached to that access point then has to share the radio resources among each other. Another one would be like your Ethernet, for instance, at least the classical Ethernet. All nodes are then attached to a cable. It's not one of these cables, but another cable we'll see in a short while. And then they're sharing the resources on that cable. Okay. Hosts can be moved around. Okay, and in particular this is Wi-Fi, but we can also do that with an Ethernet network. I mean, computers get plugged in or plugged out, especially if you have laptops, but also stationary ones could be moved around. So each network interface card, which is in one of the devices here, has, if you remember, a unique physical address. Okay, at least that's the theory. So whenever the network card inside this device was manufactured, it got a medium access control address. It doesn't change with time. It should be the same always. Now, transmissions of these wired mediums are typically pretty good. Okay, we don't have a lot of errors on these, and therefore sophisticated error control is typically not needed for these mediums. However, for Wi-Fi or wireless LANs, there's quite a lot of errors. So here we need sophisticated error control schemes. So we'll see a little bit about that when we go and talk about Wi-Fi later on in the course. Okay, LAN protocols, where they're placed, where they are in the link layer. So remember, we have the physical layer at the bottom, and then we have the data link layer on top of that. Okay, and at the bottom of the data link layer, we have the MAC layer. Okay. So now we will talk a little bit more about protocols above the MAC layer also. Okay, so and we will do this by looking at the examples, and we will talk a little bit about IEEE standards and IEEE data link protocols. So in the OSI stack, we know we have the physical layer at the bottom, and then there is the data link, and above that is the network and transport and so forth. All these 7 layers or 5 layers if you like. In IEEE 802, that's a standardization. IEEE is a standardization, and they have a committee or a series of committees called 802, and they have different standards. They have one standard for this sublayer of the data link layer called LLC, and LLC stands for Logical Link Control, so Logical Link Control, and that standard is called 802.2. And then this is a layer which supports many different medium access control layers. So we have 802.3, which is CSMA CD, or this is Ethernet. Okay. We have 802.11, which is Wi-Fi. There's something called 802.5, which is a token ring protocol. And token ring is when you have this, I can talk, and then you hand it over to the next person, right? So token, the right to talk. And there's a bunch of other LANs, but I mean, maybe these are the most well-known and maybe also the most used medium access controls. But even over like Wi-Fi, for instance, there is a bunch of different physical layers which are supported by the Wi-Fi MAC. Just as there are many physical layers that are supported by the 802.3 MAC. So here is a bunch of these. But again, it's nice to have one layer on top of this which interfaces to all of these, because then the layer above the LLC can see a unified, it only sees one interface, the interface to LLC. Okay, so these 802.x MACs, they provide a service, and that's an unreliable datagram service, meaning that data which is pushed down here is in form of frames or blocks of bits, and the medium access control will do its best to transfer that, but guarantees nothing, right? The LSC can enhance this service and provide, okay, that something that goes down into the LSC, it can provide a connectionless unacknowledgement service, which is basically just go right through. It does nothing to it. But it can also provide a reliable connection-oriented service. So this one, LLC, then establish a connection with the receiver, and then one can start to do some type of ARQ to do reliability. This is optional. And then there is another service which is closest to UDP. I don't know how often we actually use these in practice, so typically this one is the one that's used. LSC also support multiplexing of several network protocols on top of this, so it can support, say, IP for instance. That's one network protocol, but there is a bunch of other ones that could go down here, different protocols. So it supports multiplexing of these. Questions so far? No? Okay. So if we want to understand how these things work, one way to do that is to look into how the frames or protocol data units are assembled, and from that we can get an idea of the functionality, how it works. So the LLC protocol data unit looks something like this. It consists of a header and data. And this data, the service data unit, is what the LLC received from above. Okay, so this is from layer above LLC, right? So this could be an IP packet or something else. But let's assume it's an IP packet, for instance. It doesn't really matter. But if it's an IP packet, then there is a header here which is constructed. And it consists of three main parts here, the destination address, the source address, and some control. And the destination address here is something which identifies the protocol which is above LLC. So if this is an IP packet, then the source address here tells the receiver that whatever is in here is an IP packet. And then it probably goes to an IP protocol at the receiving end. Okay, so the service access point addresses here identifies the protocol entity above the LLC. So if it's 06, it's IP. If it's EO, this particular protocol called novel IPX. If it's FE, it's an ISO packet. If it's AA, this is a hexadecimal number. Then the layer above LLC is this subnetwork access protocol or SNAP. As far as I know, this one is actually quite heavily used in practice. Okay, we won't talk very much about this actually, but anyways. Okay, so then at the medium access control, what is the protocol data then? Well, the protocol data unit for the MAC layer consists of a MAC header, the LLC PDU, and a frame checksum. So what is this then? So this part here, well, it's the whole thing here. That goes down here, right? So we do some encapsulation. So LLC is above the MAC layer. So the whole thing here goes into this. And then there's a MAC header and a frame checksum on this. And the frame checksum here is to throw away frames which are in error after reception. Okay, questions? No? Okay. So one of these medium access control things that are popular is Ethernet. So Ethernet, a quick historical background to that is that Ethernet was developed before any of these ISO standards and layers and so forth were really firmly established. So it was created as a practical solution to a practical problem, right? Rather than some theoretically optimal thing, right? So it all began in the 70s, 1970s, when Aloha was invented, and that was also invented in order to support a practical problem, namely to form a radio network which was deployed in the Hawaiian Islands. Okay. Then in 73 there was two people, Metcalf and Box, who invented this Ethernet. And Ethernet is basically Aloha, but in a wireless network. That's their starting point, at least. And then this was further developed into the Ethernet we know today. So in 1979, the first standard came out, and surprisingly enough, it was called Ethernet 2. Yes?
You say that it is, as we know, that it was a random access to begin with. Is that still today, or is it scheduled?
We will see a little bit later today, but it's at the core is random access. So it's not scheduled. But there is the later Ethernet standards are a little bit different, some of them. We'll see a little bit later. But in '79 it was still random access. In '85, IEEE came on and they standardized this 802.3 LAN standard, which uses basically the same type of technology as in Ethernet, but with some small differences. And then in '95, there comes a fast Ethernet. It went from 10 megabits to 100 megabits per second, gigabit Ethernet, 10 gigabit Ethernet, 40 and 100 gigabit Ethernets. And who knows what's going to be on the market soon. I don't know actually what's going on into this community. But at least we see that the data rates have increased quite a lot during the years. And today, Ethernet is the dominant LAN standards. I mean, there are many other LANs, of course. I mean, Wi-Fi being one particular, but on the wired side, for sure, Ethernet is the dominant one. And how did it all start? Well, here's actually a sketch done maybe in '73. Okay, so what they did is that they had this medium here, the yellow thing here. This is a piece of coaxial cable, the things that were used in cable TV at the time. You know what a coaxial cable looks like, right? For some reason, they liked yellow cables. So it's not standardized, it needs to be yellow, but apparently in the beginning, a lot of these cablings were yellow. Okay, so that's why it's yellow here. So what do we do when we want to attach a node to this? Well, basically, one drills a small hole into the cable and screws in an electrical device called the tap. And then we have a connection to the coaxial cable. And when we want another station, we just drill another hole into it and attach these taps and so forth. Okay, and then we start to communicate over this cable back and forth. So that's how it looked like in the very beginning. Okay. So, but how about this IEEE 802.3? Well, basically they stepped in later on and wanted to standardize this Ethernet into something which, okay, DIX here stands for Digital Equipment, Intel, and Xerox, I think. So it's 3 companies that got together and built this standard. But then IEEE wanted to make it more like standard which was not tied to these companies. I don't know really exactly why. But they basically used the same ideas as in Ethernet. So medium access is still based on CSMA, carrier sense multiple access with collision detection. Okay, so how do we do this? Well, the basic CSMA as usual. We sense the channel. If idle, then we transmit. If busy, we sense until it's free and then transmit. So this is one persistent CSMA. Okay. Now, if there is a collision detected during this transmission, then we need to back off. Okay. Then we roll into the back off procedure, which means that we abort the frame transmission after a short while and then abort it and sends a short jamming signal. And the reason for that is to make sure that all other users of the medium are aware of that there is a collision ongoing. And then we back off. Okay, we back off a random time, and actually we back off a random number, let's call it R, of minislot times. So the actual time that we back off, the back off time is R times the time for it. R times T slot seconds. Okay, so R here is a random number. Okay, so the back off time is a random quantity. Okay, and we will see how to choose R in a second here. The critical system parameters here is the mini slot time of this T slot, and this needs to be selected such that it is more than twice the propagation time, and we will see in the next slide why this is the case, but essentially it has to do that if the we'll see in a short while. Okay, so the mini slot time is then roughly the duration of the contention period, and therefore the minimum frame duration. And this we will see in the next few slides here. So how to select this? Well, in the beginning, if we had like a 10 megabits per second medium, or this is what we transmit with, and the cable length is less than 2.5 kilometers in total. Sounds like a lot, but when you start to draw a cable around, it's not a tremendous amount of cabling actually. So I don't know if you know this, but in a modern vehicle like a Volvo or something like this, there is roughly 2 kilometers of wiring inside it, right? So you don't need a lot of space for a lot of wires. Okay, and now, anyways, so if we have this, and then we could input some amplifiers in this, and there is some time to go through the amplifier, and then I can calculate that twice the propagation time is roughly 50 microseconds. And therefore the minimum frame length was selected to be 64 bytes, and 64 bytes at 10 megabits per second is 51.2 microseconds. Okay, so the minimum length in time of a frame needs to be more than twice the propagation delay over the medium. That's important. So, and we will see why in the next 1 or 2 slides. But let's take 15 minutes.